Welcome to today's webinar, Accelerate Safe and Secure Hardware Development, Get to Know SafeTschematics for AURX. My name is Wolfgang Fuller. I'm working at Hitex Marketing in Karlsruhe, Germany. Let me shortly introduce Hitex before this webinar starts. Hitex was established in 1976 as an embedded development company and has achieved rapid growth by developing and providing microcontroller development tools. Today, Hitex as a proven expert is also in great demand as a service provider for training and consulting, test services, development and production services. Hitex supports all phases of your project from the idea to the finished system. Today's webinar will be led by two experienced experts who would like to briefly introduce themselves to you now. First, on the left, our hardware engineer manager, Günther Meyer.
Hi everyone, I'm Günther. I joined Hitex over a decade ago and have a strong focus on functional safety related hardware. In general, we do all kinds of hardware here at Hitex, from eval boards to ECUs and FPGA developments.
Thank you, Günther. And on the right, our AURX system engineer, Mr. Björn Assmann.
Also from my side, a warm welcome. I started by the end of 2017 at Hitex in the functional safety team with the focus on the AURX TC2, TC3 and so on. And I have worked on many projects from automotive, industrial and railway sector. I'm also the trainer for our product SafeTpack, the self-test library for the AURX TC3.
So I'm now at the end of my introduction. Let's start the webinar and I'll hand over to Björn and Günther.
Let us start with a short look on our today's agenda. First, we will briefly introduce our SafeTdevboard product portfolio. That shall help you to understand how our safety schematic package is able to help you. We will take a look we will talk about our safety development board, which realizes in real hardware the safety schematic reference design plus the extension board for rapid prototyping support. The block diagram shall highlight the supported features. We will take a look into the Infineon safety package TC3xx, and we will have a conclusion and some takeaways for you. At the end, we will check our webinar panels for your question, and we will take and answer a few of them. All other questions will be answered per email, like Wolfgang has already stated before, afterwards. Why are we talking today about this schematic? Independent, what is your personal or our customer product sector? Is it the automotive sector, the battery use case? Is this an avionics sector project? Is it an industrial or robotic application or a railway or train project? Always hardware is required. And in the most of the cases, a use case specific hardware is required to fulfill money, size constraints, and also to achieve performance goals. But this hardware does not just appear and can be used. Therefore, schematic is required for so many stages within the development. For the prototypes, safety analysis, customer board design, software development, configuration, and testing purposes. Most of the high-tech customer developing products or systems which must be safe and secure. To be able to achieve both goals, they selecting the best safety and security microcontroller in the market, the Infineon AURX. For example, the extremely successful proven TC3xx, which is used in a wide spectrum of product classes in a very large number in the field. Of course, each customer needs different signals and also different data processing. That is fact. It is. But more or less, most of the customers have similar work items to produce. And that is the reason why we come together and thought about how we can help and support our customers. To speed up, to improve product quality, as well as the availability, to save effort, time, and resources. We came to the conclusion, also from our daily experience, that they need a PAL, so a companion on their development journey. From the specification to the architecture, to design, and so on, until verification and production. In the most cases, a V-model approach are in use. Each company and each development team has different strengths and skills. Every development team needs a different kind of support. That is the reason why we have structured our support package to cover the whole steps. Each customer can select what they really need. That could be the guidance at the very early beginning to help to select the right AURX and further components, or the reference design for rapid prototyping with debugging support and the consideration of more or less always required minimum safety circuit, or support to select the right tools, or to set up a development workspace, or trainings and workshops for safety concept and standard compliances, or our safety pack. Our famous self-test library for the AURX, so the safety pack, supports the AURX and the watchdog and implements a lot of safety measures from the Infineon safety manual. Our AURX safe drivers, which can be used for rapid prototyping, but also for the productive use. And currently, Hitex is developing the support for the MathWorks Simulink hardware support package to empower our common customers. It is really quite impressive how fast a running demonstrator can be set up by using Hitex development board, the SafeTdevboard, our safety drivers from Safety Hall and Safety HSP together with the MathWorks Simulink hardware support package, so-called HSP. Beyond that, Hitex can support on the development, implementation, reviewing, verification up to the production. Everyone who have already worked at the safety or security projects before knows how many hours or even years and unnecessary iteration can be saved if so many information and artifact fit smoothly and smart together. So let us focus on today's headline, safety schematic. To develop a reference design, which must consider power supply, monitoring functionalities, shutdown paths, and so on, it is mandatory to start with the AURX and TLF manufacturer safety documentation. Therefore, we have considered the Infineon safety package for the TC397, as well as for the PMIC TLF 35585. Within that documentation, Infineon defines a set of assumption of use and safety mechanisms. Some of these assumption of use and safety mechanisms are realized in our Hitex safety pack, the self-test library. Therefore, Hitex has a huge experience based on the product development of safety pack itself, safety pack integration services into customer projects, as well as from the intensive safety pack training, which we also offer and recommend. Also, as Infineon Preferred Design House, we have a huge experience with the customer development projects, customer consulting and support, and we are also responsible for the development, production, and distribution of Infineon development boards and starter kits. Based on this wealth of experience, we have created a reference schematic support package, so-called safety schematic, which includes preset FMEDA, the reference schematic, and so on. For today, we thought we do not go through a schematic PDF or a long list of requirements and trace information. My colleague Günther will now show you what Hitex has realized based on that safety schematic.
Thank you, Björn. Since I'm from the hardware department, I'll start with the hardware first, the SafeTdevboard, also referred as the TC397 SO-DIMM. Our goal is to create a functional reference design out of the knowledge of safety schematic. This means we want to give you a guidance and support to work with SafeTpal and the AURX platform in general. The SafeTdevboard has a DDR4 SO-DIMM form factor with 2 mm of component height on each side, so it's very slim and very neat to use. It is powered by either USB-C or the SO-DIMM connector. As microcontroller, a TC397 is used, and the TLF 35585 is the power supply and watchdog chip. It features several different interfaces, such as PWM for motor drives, analog to digital converters, inputs, SPI, or simple GPIOs. Also, we have Ethernet and an onboard debugger available. I'll show you a block diagram in a second, but let's have a quick view on the whole hardware platform. Besides the TC397 SO-DIMM on the right side, we have the generic breakout board on the left side developed. This will make you a quick start into the AURX and SO-DIMM designs. It acts as a carrier for the TC397 SO-DIMM. It will give you a flexible interface to all available IOs of the SO-DIMM header. In addition, the breakout pin headers in the center of the board, we have CAN, external Delta Sigma IDC, potentiometers, and RJ45 Ethernet jack with integrated magnetics, and 2 microbus headers for additional expansion. But let's have a look into the block diagram of the TC397 itself. So the 2 main components are the AURX and the TLF35585 and its interface in between. Powered by USB-C or SO-DIMM, the TLF35585 itself powers the AURX. We have a mini wiggler and a DAP connector to debug and flash the AURX. 24 PWM outputs or timer inputs, of which 9 are complementary PWM, are also available by using the dead timer modules of the AURX GTM modules. Also, incremental encoder support is realized using GPT-12 modules. Up to 64 analog inputs are available, and also widely known interfaces such as QSPI and ASIL-D modules. The ASIL-D modules can either act as SPI, UART, or in LIN mode. We have CAN modules connected as well as SEND and simple GPIOs. An onboard Ethernet PHY is connected to the internal MAC of the AURX and is capable of 100 megabit Ethernet. In the future, an automotive 100 base T1 interface is planned. In addition to that, we have, of course, some LEDs, push buttons, and a reset button. Let me introduce you to some parts in detail and start with the debug interfaces first. The accessibility to the AURX is realized by different interfaces. We have the onboard debugger, the mini wiggler, or a DAP connector for direct access to the AURX debug engine, the OCDS. The mini wiggler is connected by USB-C and features also a virtual COM port to print out debug messages using an ASIL-D UART module. Depending on the selection of the configuration header drawn on the top right corner, the internal generic bootstrap loader can be used to flash the AURX as well. The bootstrap loader is using an ASIL-D module of the AURX and is made available at the SO-DIMM interface. The TLF35585, however, acts as a watchdog chip. It is in constant communication with the AURX in a long open window scheme, which expects a continuous triggering. This means if the TLF is not treated correctly by the AURX via SPI, it will simply reset the microcontroller and start over again. To prevent this during development or flashing of the AURX, a user needs to actively shut down this safety watchdog behavior, either by special SPI messages directly at power up of the system, or by strapping a hardware signal, the MPS pin, to appropriate levels. Now I'm about to show you the minimum safety circuit of the AURX and the TLF chip. So there are several connections necessary to start implementing functional safety for this hardware platform. The TLF35585 watchdog and power supply chip will monitor the AURX, generate and supervise the power rails for the AURX as well. Also, it acts as a second shutdown path to an external circuit. As stated before, AURX and TLF35585 communicate via SPI in either a window watchdog or a challenge and response scheme during runtime. That means they monitor each other all the time. So let's have a more detailed look into that setup. This picture shows the monitoring functionality of the TLF 35585, as well as modules that need to be triggered and controlled by software from the AURX. And this is where a safety schematic will support you to make functional safety implementation of the AURX platform as easy as possible. Therefore, we have a safety pack developed to handle the AURX and TLF communication and to trigger and treat AURX and watchdog self-tests. This will cover a lot of the blue marked items on both the left and the right side. The TLF itself is monitoring the power rails it dwells, and in case of an error, it will reset the AURX and trigger safe state output pins. If we move forward to the next slide, we have a look into the extendable safety circuits of the TC3xx SO-DIMM. The functional safety implementation does not need to end with the AURX and the TLF communication. We can also use the IOs of the SO-DIMM connector to help you achieve a safety goal while directly using our hardware platform. However, this needs to be properly analyzed according to functional safety standards and to your safety requirements. Besides the hardware, the safety schematic offers even more. Therefore, I will hand over to Björn.
Thanks a lot, Günther. I think this is a quite impressive hardware platform, which really helps our customers on rapid prototyping. So we have already used the term Infineon safety package. Infineon as a manufacturer of the TC397 provides a zip file with here are left depicted content. You see at the beginning of the package name, it is an AURX TC3 family member dependent content. Here for the TC39. It contains few application notes, the datasheet and the datasheet addendum, the errata sheet, the FMEDA calculation files, the safety case report, safety manual, which contains safety mechanism, assumption of use, and so on, the user manual, and the release note and support documents. For the automotive, this package is available as the ISO 2626 2018 safety package, and for the industrial sector, there is an IEC 61508 2010 safety package available. Both are more or less equal and differs only at the FMED Excel calculation file and an additional addendum for the safety manual to take care for the IEC 61508 deviation towards the ISO standard and variant. Because these few files are different, a dedicated release note is required and provided as well. So this FMEDA Excel calculation file we have also pre-set up to save time and to improve your customer support. Let us take a few seconds about errata documentation. Infineon has introduced for the errata documentation a dedicated name scheme which helps on evaluation, tracing, and collaboration. The first information is related to the module or aspects. So ADC generic timer module or safety aspects, for example, followed by an information about the architecture. So it's a tri-core related or multiple architectures like tri-core and XMC. Also an indication is there if this is a parametric deviation, an application hint or documentation update. And at the end, there is a number to ensure uniqueness. It is quite important to analyze that errata sheet document and also the updates on that documentation by Infineon. Why that is so important? Let me give you just an example. The following real support case from a Hitex SafeTpal customer, which I have worked on. The message was, we have produced already a huge number, if I remember right, more than 10,000 pieces or so. of customer boards, but we see now that the system stucks and is not able to boot up correctly, although the ASIL-D fails. Help, panic. Really panic. So the provided customer configuration for the HTX LBIS test we have checked, absolutely fine. Therefore, we had a remote session with them to be able to debug the customer issue, and yeah, we have checked also the customer schematic, and we figured out that the clock signal of the DAP connector was connected too high, so pulled up. You can see here in the description of this hardware router that the clock signal on the DAP connector, if it is pulled up by an external device, LBIS execution will be stalled. That is the reason why they have stucking LBIS and not correct booting up system. Such a late hardware issue is an absolutely nightmare for reputation, money, time, and leads to huge frustration on all levels. Therefore, we provide our reference design, the SafeTschematic, which takes already care for this and other errata, as well for the generic set of an application assumption of use. Hitex does not know the final customer hardware. Therefore, we recommend to check the errata also for your specific schematic and PCB. If you start with your customization of our preset up FMEDA to adjust to your customer hardware, we recommend the following first calculation steps. For the FMEDA Excel file, you need as an input the base failure rate calculation results to determine lambda die and lambda package. That is mission profile dependent. 2 base failure rate calculation sheets are available by Infineon, the withdrawn IEC 62380 and the Siemens norm SN 29500. To be able to calculate use case specific FMEDA results, the base failure rate calculation are required and is an input. So let us take a look into the Excel file. Here on the left, it is the IEC 61508 FMEDA version depicted. Just for starting purposes, open the result overview sheet to configure the minimum startup setup. Calculate your specific mission profile with the dedicated base failure rates and enter or type in here the values for the lambda die and lambda package. Adjust the package type and then continuing with the flux factors. First with the flux factor for neutron particles. For field usage scenarios at a sea level, keep 10 as a start point. Later, you have to adjust in accordance with the JSD89A reference calculator. Here on the right side is the link depicted, the appropriate value. This value will depend on the altitude and geolocation and so on, and will have an impact on the soft error rate. If the altitude is higher, your soft error rate will be increased as well. Alpha particles, you have to keep the 10, the pre-filled one. This is no geolocation dependent, it is related only to the material of the microcontroller package. Before you use any FMEDA results, ensure by pressing the recalculation button of Excel that they are really up to date. Further, you must analyze for your use case specific hardware schematic which pin you have in use, which are GPIO, so generic purpose input-output ports, which are not in use by a GTM or a QSPI module. Here we recommend to respect the Infineon comments, which guides you already. With that, you achieve a first rough FMEA result by your own. So let's sum up and talk about the takeaways. You can benefit from our huge experience with the AURX development projects. You can empower your resources to work effectively within AURX projects. You can avoid unnecessary iteration of V-model phases. You can focus on the important clauses and system constraints. You can more focus on your application IP. You can accelerate time to market with confidence, and you can take the advantage of both standardized and customized workshops and our packages. If you want further details, I would like to ask you to go in contact with my colleagues from sales. So here, Michael Weiss, our senior account manager, and also Aranyan Ravanan is our sales FIE. Here is also a direct link to our SafeTdevboard information page or a QR code to try the same. But we have also further webinars about our SafeTdevboard product portfolio and packages. Few of them are already presented, but you can see we have also upcoming webinars, so stay tuned. Via the QR code, you can watch the already recorded sessions. And now I'm looking forward to your questions. So Wolfgang, you have checked during the session, hopefully, the chat panel. Do we have any questions so far?
And we have a few questions, and I will try to pick out some which may be of general interest. First one, which voltages are supported by the SO-DIMM for the pins? Maybe a question for Günther.
Yeah, sounds like. Yeah, so right now the SO-DIMM that I have shown is a 3.3 volt only design. However, the TLF 35585 is also available in a 5 volt variant. This means right now we have 3.3 volt for the IOs, for the digital IOs, as well as a 5 volt capable analog inputs, but also a 5 volt digital IO and 5 volt analog input version would also be possible. Please note that also protective measures for IOs, for example, should be available on a carrier board. So if you plan to integrate SO-DIMM directly into your design, this is something that you might want to make sure, and we should have definitely a chat about it.
Question 2 would be here, is a bit longer, I think. Thanks for the good presentation. There was ISO 26262 and IEC 61508 safety package stated. Is there a dedicated package available for other product sectors? I ask because we currently are working on a railway project. Yeah.
The railway standards like the Canalec 50126 for hardware or Canalec 50129 for systems, very often referencing and using the IEC 61508 standard. Therefore, we had in the past used the 61508 safety package and the Siemens norm SN 29500 for the lambda calculation and for the with this IEC 61508 AURX FMEA Excel file, we have calculated then the safety matrix and the fit rates. If you have any further questions, send us an email.
Okay. And question number 3, where will the SO-DIMM be available, or when or where?
I can answer both.
Yeah.
So first, it will be available soon. So you have seen the real picture of it. So it's available already in-house, but it's undergoing currently testing. As soon as it will be available, will find it under our eShop at www.hitex.com. Or you might want to contact Michael from our sales team. He will be happy to directly support you in that case.
Okay, thanks you. The fourth and I think the last question we do today is to Björn. You have presented the FMEDA Excel sheet. It seems that they are not the pre-set up FMEDA for the safety schematic. Is that right?
That is right, absolutely true. The intention from today's webinar from my side was to give you an understanding what a safety schematic is, but also to give you already some benefits. So you should have already access to the Infineon safety package. And with my small first hints, you can start today to adjust your FMEDA to your customer hardware, to your schematic. This was the intention. But yes, in the safety schematic, we will have these preset up FMEDA Excel sheets fitting to the SO-DIMM.
Thank you very much to both of you, Björn and Günther, for being here with us. Bye-bye.